So I will now start with one update. So in the first session, I mentioned some resources which I consider useful for users of Fiji or ImageJ, and I have added one more resource today to this list, and it's a website called Bioimage Informatics Index. I will show you how does it look like. It is a sort of website to search different tools for obviously bioimage analysis. It doesn't apply only to Fiji or Fiji plugins, but there are of course also plugins, Fiji plugins listed among the tools. It's not yet fully comprehensive. I checked, I looked for some plugins which I know of, and I found some. I didn't find others, but if people keep posting their tools here, if it becomes an established feature for all bioimage analysts who are developing new tools, then it looks like a potentially a very useful tool which will allow you to search for tools not only in Fiji but also tools for plugins or other programs. So then let's go back to the topics. And last time we talked about segmentation in images, and I talked mostly about segmentation in 2 dimensions. So let's briefly get back to the topic of segmentation and look a little bit more on segmentation in 3 dimensions. So I'll open Fiji, and let's open one of the sample images which we have already used in the past, and it's this image called confocal series. There are 2 channels, different number of sections, and let's look at this channel which is displayed in green, which is something that looks like a nucleus or a cell. So I will do again image, color, split channels. I'll close the red one and I keep this one. And if I want to, because now this is not it is a 3-dimensional image, it's a stack 3-dimensional, so there is a 3-dimensional object. So if I want to segment this object, I can of course do the same what we did last time. That means to use the threshold feature and then threshold the object in each plane, and then do an analysis in 3D. I can also use here a feature which is called 3D object counter, which is a little bit of a counterpart to the feature called analyze particles, which we used in 2 dimensions. But in this case, this tool does the thresholding as well as the counting and the analysis of the objects. So I'll open it, and you see it already set some automatic threshold. So if I then go through different slices, I can check how the object has been segmented in different slices. I can of course adjust the threshold, or I can accept what is the automatic threshold offered here. You can see one disadvantage in this case is that I cannot choose the thresholding algorithm. It uses some default one. I'm not sure which one. I cannot choose a different one. What I can do similarly to the 2D version, I can set limits, lower and upper limits on the size of the object. And I can, for example, exclude objects on edges, similarly to what we did in 2D. And now if I press OK, I let it process, and it comes with some results. So here, this is not important there, but here are the results. So I have the volume of the object, the surface, and some measures of intensity, maximum, minimum, median intensity, and so on. I can have also some images here. This is the map of centers of mass of all the object. In this case, it's not a very interesting image because it shows just the center. We have only one object here, so it shows just a single point. This centroid, so that would be similar. This is the surface of the object, and this is the binary image of the object. So this is one way how I can do it. If I want to use, let's say, the default thresholding algorithm here doesn't work well for me, I can still use what we did last time, image adjust threshold. I can use an arbitrary algorithm from the list, and I will get a binary stack, and then I do the, we can try to do this, image adjust threshold, set, and then in case I have a three-dimensional object, I can use not the histogram of individual array of individual slices, but the whole stack histogram, and then I can choose different algorithms. Apply. And we will calculate threshold for each image. Okay. And we got, in this case, I made a mistake here because I had here selected, I have dark background. Again, open samples, open series. Channels, image adjust threshold, and background. This one looks okay. Y. Fine. Okay, and now if I go here, analyze 3D object counter. So in this case, it doesn't really matter the threshold because this is now I have a binary image. So that means that the object has the value 255 and the background is 0. So I can set the threshold to any value between 1 and 254 basically. And here we go. And if you remembered what was the volume last time, so now we have a larger volume because we used a different thresholding algorithm, which so the differences comes from two things. One is that the thresholding slightly made the object larger because it set the threshold lower, and also previously there was a hole inside of the object where the intensity, there was one part, or maybe the nucleolus, where the intensity was lower, and that was excluded from the object. And now in the current thresholding, that is also included. So that's why the volume in this case is larger. So you can see that how tricky this might be if you compare the volumes. You have to use consistent way how you do the segmentation, how you set the thresholds to get comparable results. Otherwise, if you don't use the same algorithm every time, you might end up with large differences, artificial differences in the volumes. Let's close this. And of course, these I was using now features which I believe are included in Fiji distribution, but there are also other tools, other plugins developed by other groups which do similar things. So for example, I have downloaded here a plugin or a suite of plugins called 3D, which contains all sorts of functions for segmentation in 3D. So, for example, what we did for the binary masks in 2D, like we fill holes, or did watershed algorithm to separate objects which were touching each other. So this can be all done in 3D. So if you are doing 3D segmentation, this might be a useful tool for you to use. And then I go here to plugins, 3D, now 3D manager. And now I will do the segmentation, plugins, 3D. I can use, for example, here this nuclei segmentation, which will allow me to select different thresholding algorithms. Or I can set a manual threshold as well. So let's try some, for example, Otsu. Okay. Let's wait what comes out. Doing something. Okay, now you see that maybe that wasn't the optimal threshold, because it segmented some parts which are outside of the object. So ideally, I should now go back and try to use a different thresholding algorithm. But to save time, I'll just use this and show you. So I here add image. This is now I can do different things like measure 3D. That should give me the measures like volume, surface, and all that for the segmented objects. See if I can in parallel, before this is done, if I can see, I can also see this object in 3D viewer. So I can try to see this in the meantime. And yeah, so this is the 3D viewer. I could here, in principle, I could rotate the object, but it's a bit slow because it's still doing something. And here we come. So this is the object. So there's somewhere there's volume and surface area, so on. So this is another plugin or collection of plugins which you can use in case you are working a lot with 3D objects. Where can you find the 3D plugins? A good question. They don't come with, if you install Fiji, they are not included automatically. So you have to do, if you watched our last week's session, so I showed that if we run update, then we have an option to select update sites. So the developers of the plugins can add can create an update site for their plugins, and you can select automatically to update, to manage update sites, and you can select which plugins you want to be installed and automatically updated. So here is this 3D image suite. So if you select this, check this option, then the updater will install, if you don't have it yet, will install these plugins, and later will check for updates to keep them up to date. Let's look at another topic, which is Fourier Transform in image processing. So this is something more related to what we did before, segmentation, and that were all those things like filtering images, removing background, or denoising of images. So we used different filters for that. And for example, we removed the background using rolling ball algorithm. And similar things can be done using Fourier Transform. But before I get to that, let's briefly explain what is the whole idea of Fourier Transform. So I prepared an image here. So normally we look at images in a spatial domain. That means that we see where different objects, different features are located in space. And that's a natural way how to represent things, because that's how we, when we are looking with our eyes, that's how we see the world, and that's how we expect images to look like. So for example, if we have an object like a grid, then we expect to see that there will be a periodic pattern of lines. Let's say in this case, we have a periodic pattern of lighter and darker lines. If you want to see the profile of it, then I can analyze plot profile, and you see that it is actually a sinusoidal pattern. Another way how we can represent images is in frequency domain. And that is something which is not very intuitive, because that's not how we see the world. But it's an equivalent way how we can represent an image. So instead of showing where the features are in space, we can show what is the distribution of spatial frequencies in an image. So in this case, instead of saying that we have a stripe, light stripe here, a dark stripe here, a light stripe here, a dark stripe here, so we can say that we have stripes which are vertical and they have a certain frequency. And that's an equivalent description of this image. It is quite natural, or at least reasonably natural, for an image of a periodic structure like this one, because that's something where it's quite logical that we might describe it using spatial frequencies. That's why I'm showing this image here. Not so obvious it is that this spatial frequency description is applicable to any type of image, because any type, any distribution of objects or any distribution, can be described by a sum of harmonic periodic functions. So even something which is not periodic at all can be described as a sum, a series of periodic functions. Of course, if it's something which is not periodic at all, then in principle we might, to fully describe it, we would need an infinite series of harmonic functions. But it is, in theory, possible. That's the whole idea of getting images, having the frequency images represented in frequency domain. And the Fourier transform is basically the transform which transforms images between the spatial and frequency domain. So if I if I take this image, and here I do process fast Fourier transform, I will get an image, a representation of this image in frequency domain. And you can see that it looks quite simple, which is not surprising because I have here something which is perfect, nicely periodic, harmonic on top of it. So you see here that everything is, the whole frequency spectrum is located along one horizontal line, because here all the frequencies are, or the periodicity is in horizontal direction. So that's the reason. If I flip this image 90 degrees, then I would have the whole frequency spectrum along a vertical line. I cannot see here the spectrum, so to see it, I will do again plot the profile, analyze, plot profile, and what you see here, I have here a central peak which corresponds to 0 frequency, that will be always there, and then I have 2 peaks which correspond to the frequency of these sinusoidal functions, and there are 2 of them symmetrically, because I can look at it that there's a positive frequency when I go from left to right, or a negative frequency going from right to left. So that's why the Fourier spectrum is symmetrical. You may see that there is a little bit more to it than just these 3 peaks. You see there is some sort of envelope to it, and that comes from the fact that this image is not infinite. So if I had an infinite image, an infinite sinusoidal, then there would be indeed only 3 sharp peaks. But because this image, the image has some beginning and an end, which means it's basically a step function here at both ends. So that's why I need to include some content of higher frequencies to describe the end of the image. I will keep this here, and then I prepared one more image, which is very similar. It just has a higher spatial frequency. So I do the same process, Fourier transform, fast Fourier transform. You see the spectrum looks very similar. which is not entirely surprising. And now I do analyze, plot profile, and you see it looks very similar, just the two peaks are shifted to higher frequencies, which is what I expected. I have here the stripes with higher spatial frequency. Now, you might be wondering, what would it look like if I take something which is completely non-periodical? I can generate such an image, file, new image. Now I generate something which is not file, new image. I do it white. And then I will basically generate a step function. My step functions here. So now I do process. And you see, well, it looks again very similar. Why? Because all the information here again is in horizontal direction. But now if I look at the frequency spectrum, analyze, plot profile, so you see I have now, it looks very different because I need to have much higher content of higher frequencies to describe something which is not periodical, and some more it has a very steep edge. So now you might be asking, what is all this good for? But before we get to that, let's look how does it behave a little bit. So again, process, Fourier transform. And now I might do one thing. I might just delete part of the spectrum. So remove some of the spatial frequencies. So what I do, process, transform here, a tool to make a circular selection. So I will do, for example, something like this. Okay, I clear outside. So what I did, I basically removed all the higher spatial frequencies. Now I do process, inverse, Fourier transform, and what you see here is that I see some blurring of the edges. I can show you the profile. You see that I have here some blurring of the edges, and I have here some periodicity which is starting to be modulated on the original step function. And this is what comes from, because I removed these the highest frequencies which were needed. So to describe a steep edge, you in principle need infinite series of periodic functions. So if I remove the highest frequencies, I will be losing I will won't be able to describe a very sharp edge. So the edge is blurred, and on top I'm starting to see some periodic modulation. I can do a similar trick with the periodic functions. So process, fast Fourier transform, process, filters, make circular selection. So I try, for example, the same radius for simplicity, edit, clear outside, and what I will do now is process FFT inverse. And what you see is that I have, of course, still a harmonic function, but the modulation is reduced. And now you might find all this frequency domain as something which is purely a mathematical construct, that it has very little to do with actual microscopy and optics. But it's not entirely the case, because there is a discipline in optics, a way of, say, this, how to describe optics, which is all based on Fourier transforms, so-called Fourier optics. And actually, if you have an imaging system, if you have lenses, then what is happening, then if you know that when you image something using lenses, you will get an image which should look like the object in spatial domain. But if you look at different planes at the image, you might find out that actually you might be getting a Fourier transform of the object. So this is something what is actually happening in optical systems. And you probably heard many times about resolution of optical microscopes, about the diffraction limit. And you know the description of this phenomenon in spatial domain, where you know that there is some point spread function. So if you image an infinitely small object, a single point, the image won't be a single point, it will be broader. It will be a point spread function of the microscope. And then if you image an arbitrary object, the image will be a convolution of the object with the point spread function. An alternative way how you can look at it is in using Fourier transforms. And you may say that what the aperture, the numerical aperture of the microscope is doing, it's basically causing a cutoff in the frequency domain. So it is doing the same thing what we saw here, that we are losing some of the higher frequencies. And that's why you could see that this is also causing blurring of the images, and also a loss of contrast for high frequencies. If I proceed further and make this even smaller, process, filters, make circular selection, so I go third, make it even smaller, edit, clear outside, and now I do process, inverse FFT, and now you see I can't resolve the stripes anymore, because my numerical aperture is too small. So the stripes got below the resolution limit. So you see that actually the Fourier transform is something which is very closely related to how images are formed in a microscope. And I mean, you might be wondering, what is the relationship between the describing the image formation through Fourier transforms and the convolution of this point spread function? And it's actually also very tightly related, because a convolution in spatial domain is equivalent to a product of two functions in frequency domain, in the Fourier domain. So this is just to give you a little bit of idea that this is not something which is entirely just a purely mathematical construct, that it's something which is actually closely related to what is happening in microscopes. And now how we can use it in image processing. So you see, one obvious thing is that when I am when I was doing removing the higher frequencies, so I am blurring the images, so I am removing high frequency content. So if I remove high frequency content, it's basically smoothing the image. So this is something very similar to what we did when we were applying, for example, Gaussian blur or median filter on images. So I can show you, for example, here I can do process noise, add noise to this image, and then I do process, and I have here under the Fourier Transform menu, there is an option to define filters. So I can say that I want to limit now the high frequency, but I just want to remove small features. I don't know, let's say 2 pixels, and we don't want to suppress and stripes now. So this is how the filter would look like, and this is the image. You see that it's not that great, because, so I would say that for removing high frequency noise, I personally find the spatial domain filtering a bit better. We can try to compare. Now process filters, median filter. I personally find that the spatial domain filtering is a little bit better for removing the speckle noise. But there are other, so I can do the opposite thing, and I can use Fourier Transform to remove uneven background. So that's what we did, similar thing like what we did with so that's a similar thing what we did with rolling ball algorithm. And I can use, so this is you can find it if you go here, open samples, and this is called 3 rings. So that's the image which I want to use now. So I can process FFT, bandpass filter, and now I don't want to remove any high frequency noise, but let's say I want to remove low frequency, so components. Okay. This is the filter in this case, and you see that I'm basically flattening the background, because the background that's something which is stretched over larger distances, so that means it has lower spatial frequencies. So I would say I find I like the spatial filtering a bit better for high frequency noise, but I find the frequency domain filtering that it is quite nice for low frequency removal, that means for background removal. But there's one more thing I want to show you. So unlike the spatial filters which we used, and they were isotropic, so they basically didn't make difference between the different directions in the image. You can of course do anisotropic spatial filters, but you don't have them readily available. You would have to program them yourself. But in Fourier Transform, this is something which comes in a very straightforward way. So I do process, FFT, and now this is the Fourier Transform, the frequency domain representation of the three rings. And you can see again that I have a prominent horizontal line, because I have, let's say, high frequency content along the horizontal line. I have a lot of features there. And then I have some less prominent features which are along the vertical direction, and some which are slightly tilted from the vertical direction. And you can notice that one feature which is very prominent and which is close to horizontal, this feature means it's it contains frequencies along the vertical line, are these cracks in the wood. So I can specifically try to remove them. So I basically want to try to remove everything which is close to horizontal. Opposite direction. And now I do the inverse Fourier transform. And you see the difference in the image. So you see the difference that now I have very much suppressed the crack in the wood. Of course, I've also lost, here in this case, I have part of these rings which are horizontal, so I've lost them as well. But it's just to show you that how Fourier filtering can be used to remove features which appear along particular direction. How did I delete them? Well, I just selected the regions of interest and I pressed delete. That's what removes, that basically clears the region of interest. So it's the same like in what I can do in an image, because the frequency domain image is just like any other image. Press delete button. Okay. So that's for Fourier transform. And maybe it is a bit of something which is not so intuitive, the Fourier transform, but it is quite interesting for image processing, and you can, if you want, you can try to play with it, and you might find that it does some, it can do quite interesting things. And the next topic, big topic, and topic which is one of my favorite topics in image processing and analysis, and that is colocalization analysis. So before we do here demonstrate how to do colocalization analysis using two different tools in Fiji, let's look more at the different colocalization metrics, because I know that sometimes people are a bit confused and they don't know which metrics to use and how to understand them. So the most commonly used metric is Pearson correlation coefficient, which is usually denoted R, either lowercase or uppercase r, and it can have values from -1 to +1, where 0 means there's no correlation between the two images, so everything is random, and +1, that means it's a complete colocalization, so that means you basically have two identical images, and -1 is anti-colocalization, so that means where you have high signal in one channel, there is low signal in the other channel, and vice versa. Here is a formula. I don't like showing formulas because it usually doesn't explain much, so don't bother too much about the formula. I'll better concentrate here on these images by which I want to illustrate what is the meaning of this formula. So I'm not showing here an image, but I'm showing here something what could be a line profile. If you draw a line in an image and you plot the profile, the intensity profile along the line. So I have two channels, red and green channel, what I did at first is that I subtract the mean value from the image. So that you can see here that now I have values which are negative as well as positive. So negative means that those are pixel values which are lower than the average pixel value. So this is what you see here. From each pixel I have subtracted the mean intensity. And I do that for both channels. So then, so these are the mean subtracted line profiles. And in this case, there is clearly colocalization between these images. So where I have high signal in red channel, there seems to be, in most cases, high signal in green channel as well. And where I have low signal in red channel, there is low signal in green channel as well. So then what I do, for each pixel, I do a product of these two values. So I multiply the green value with the red value. So then you see this is what I get is then this blue curve, because which is systematically higher than 0, systematically positive, because when the red channel is positive, the green channel is also positive. So I have a product of two positive numbers, which is positive. Where the red channel is negative, then the green channel is also negative. So I have a product of two negative values. So again, a positive value. So that means the sum of all, if I do the sum over all pixels, I will have a positive value. On the other hand, if I look at the line profiles from an image where there is no colocalization, so you see I have high value in green channel, but relatively low value in red channel, I have high value in red channel, low value in green channel. Doesn't seem to be any systematic similarity between the two profiles. And then if I calculate these products, it is the magenta curve, and you see that, of course, I have sometimes there is a positive value, but sometimes there is a negative value, and mostly it will be somewhere close to 0. So in this case, if I calculate the sum, I will have probably some very small number which is close to 0. And then the denominator, this is nothing, this is just a normalization. So that I get +1 for perfect localization and -1 for anti-colocalization. So this is, otherwise it would be plus some random value which will be different depending on the intensities in the images. So this is just to make the Pearson coefficient independent of the overall intensities. So that's Pearson correlation coefficient. It's a very popular way how to characterize colocalization. It is easy to calculate, and it is quite robust against background, because you see I calculating here these products. So that means pixels which have high intensity will contribute much more to the sum. Like here you see where I have high intensity, so this will shoot up in the product. So this will contribute a lot to the sum. While pixels which have low values will contribute very little. So that makes it robust against background. Background doesn't, even if there is some colocalization in the background, it doesn't really affect too much the value of Pearson coefficient. On the other hand, there is a little bit of danger that if I have some features which have extremely high intensity, so then they might increase the Pearson correlation coefficient a lot. If there are, of course, colocalized high intensity features, and they might result in quite high Pearson correlation coefficient, although there might be no colocalization in majority of the image. Then another commonly used metric are Meanders split coefficients, which have they are, let's say, complementary to Pearson correlation coefficient, and then they describe something very different. So here, this is not a one value, there are two coefficients. And the definition is such that I am looking at the intensity in pixels, red pixels which colocalize with green. So that means here I am only taking those pixels in the red channel where the green channel is above a threshold. So here it's extremely important that the threshold is crucial. So let's say if you set the threshold to 0, you don't set any threshold, then of course, and your image has some non-zero background, so that means that all the pixels have a positive value. Maybe the background will have a very low value, maybe 1, 2, such low values, but it's larger than 0. So then you would have, means you would take all the red pixels. So you will end up with a very high coefficient, which doesn't mean anything. So you have to really the way how you set the threshold is absolutely critical. Unlike in Pearson, where you don't need to bother about a threshold much. So this is not answering just like are they colocalized or not, but this is saying what is the percentage of red signal which colocalizes with green signal. And I'm trying to illustrate it by these two images where I have some yellow pears and red and green apples. So you see that in this case, both of these coefficients are something around 0.6, which means this is the percentage of the pixels which correspond above threshold pixels which correspond to these pairs, because the apples are not, there's no colocalization in the apples, only in the pairs. Now, so both of these coefficients are roughly the same because I have one red apple, one green apple, so it's a symmetrical situation. But now what I did, I removed one of the apples, and in this case, it's no more symmetrical. So you see that one of the coefficients stays the same, but the other coefficient is now 1, because there is no green signal which is not colocalized with red. I hope I managed to explain it somehow to you. What is the meaning of these Meanders coefficients? So basically, if I have an excess here, in this case of this coefficient, I basically don't care about the excess of the red signal. I'm just asking what is the percentage of the green signal which colocalizes with red. And the answer is 1, because there's no green signal which is not colocalized with red. So these Meanders coefficients, they are answering a slightly different questions than what the Pearson coefficient can answer. Let's not confuse you further for now, and let's try to run some colocalization analysis. And then we go, then I'll show you one more colocalization metric. And let's start with something very simple, though quite artificial. That's the pear and apple image. And I can use, for example, something which is available in Fiji. Under colocalization, there is a tool called Colloc2. And it requires the two channels to be separate images. So I go back and I do image, color, split channels. And now I do analyze, colocalization, Colloc2. And I select channel 1 and channel 2. And now so I mentioned that for these Meanders coefficients, threshold is very critical. So there is a way how to automatically determine the threshold, and that's so-called Costa's algorithm, which works that way that it is setting the thresholds in both channels iteratively, starting from higher value and then going down until it finds a value below which, so when it reduces when it looks at the pixels which fall below the threshold, there is no positive correlation, no colocalization between those pixels. It's quite popular. In many situations, it works quite well. It won't work if there is it requires that there is a positive correlation to start with. So if there is even for the whole image, if there is no positive correlation, then Costa might fail. And in some very pathological types of images, it also might fail, such as these, which are, I mean, they are totally artificial images. So here, Costa doesn't work very well. And let's do we don't want to save it, but we want to see the output. And one thing what you see here, this is so-called two-dimensional histogram. So it is a very useful graphical representation of colocalization. And what it shows, so here, this axis, those are different intensity bins in one of the images, and these are different intensity bins in the other image. So that means that if I have here this cluster, so this is the background, because in both there is no value in both channels. These pixels, this cluster which lies along the line, basically a line of proportional line, that those are the colocalized pixels. Because if I have the higher the intensity in first channel, the higher the intensity in second channel. And then this cluster, those are the pixels where I have low intensity in channel 2, but high intensities in channel 1. So this is basically object which is only in channel 1. And this, again, is only an object which is present in channel 2. So this is, I mean, this image I generated in such a way to show you all these different types of clusters which I can see in the two-dimensional histogram. So I have something which is only in channel 1, something which is only in channel 2, something which colocalizes, and some background. We can then later look at more realistic images, and you will see that there are, of course, still all these features, but they are not that clearly not that obvious and clearly recognizable as in this case. And then I can look at these different values. So let me navigate to something. So Pearson coefficient 0.54, which is not surprising. I have roughly half of the features which colocalize. So these two pairs, there is the colocalization. And then I have here Meanders coefficient. So if there's no threshold, so then of course both coefficients will be equal to 1. So that doesn't say anything. But then if I have a threshold, then you see then both are something around 1/2. So that's something quite meaningful. I can then do what I did in the example. I delete one of the apples. I delete the green apple. And now I run again, analyze, colocalization, colloc2, and channel 2. Okay. Is there any problem? Analyze, colocalization, okay, I see. I selected a wrong image. So now it should work. No, it doesn't. one is don't want any masks there. So hopefully, oh, now I see. Okay, I was setting in a wrong field. So this is a field for a mask. So you can only analyze, you can draw a region of interest and only analyze a part of the image. So that was my mistake. And here we are. So you see that the histogram has changed. We don't have the feature which was only in channel 1, but not in channel 2. And then we look at some of the metrics. Pearson coefficient increased to 0.75 because I removed one of the objects which were not colocalized. And Meanders coefficient, now you see it's not symmetrical. There's an asymmetry. One of them is higher than the other. So that's what we want, what we expected. Now let's comment a bit more on this colloc. So there is one more feature here, which is also related to the same authors as the threshold regression algorithm, and it's Costa's significance test. So that is it's a method how to test for the significance of the colocalization, to show that this is something which is not random. And it works in a way that it takes one of the channels and splits it into segments, the image, and reshuffles the segments. And then it calculates again the colocalization and does the reshuffling many times. And then it gets a number of values for the differently reshuffled images. And then it's looking if the colocalization in the original image is statistically significantly higher than in all the reshuffled images. And if there was a real colocalization, then it should be significantly higher than when I randomly reshuffle the segments of the image. So that's how it works. And why is there a point spread function? So the idea is that ideally I should choose the size of the blocks to reshuffle according to the point spread function. So that's why we can select here point spread. We can set here the point spread function, a number of randomization. So the higher the number, of course, the longer it will take, but the more meaningful the result and the stronger the result. There's one more colocalization metric here which you can calculate, and this is this Lee ICQ, which I'll show you here. This stands for intensity correlation quotient, and it's another colocalization metric, which is defined in such a way that it's a bit similar to Pearson coefficient. So again, you see I am calculating a product of the mean subtracted images for each pixel. But then what I do is I don't sum it up like with the Pearson correlation coefficient, but I take the number of pixels where this product is positive and divide it by the total number of pixels. And then I subtract 0.5 so that for random image, I will get, where there's no colocalization, I will get a value close to 0. Here you can see examples. So I generated again 2 artificial images which show a gradient in intensity. So if the gradients are the same, means I have high colocalization. So then you can see the ICQ is 0.39 and Pearson correlation coefficient is 0.9. So now you might say that this is, so that in this case, the maximum is for fully colocalized image is 0.5. So you might say that 0.39 is not that high value. You might expect something higher for images which should be very highly colocalized. The reason for this is that in this case, there is because I've added some noise to these images. So here I have a gradient. So the value here in along the center line. So that's about the average. Here I have the pixels which have the average value, but because I have the noise, so I will have a number of pixels which are slightly higher in one of the above the higher than the mean, but in the other channel they might be slightly lower than the mean. So they will then reduce, all these pixels will reduce the value of ICQ, but they won't affect the Pearson correlation so much because the differences are very small. So the products are relatively small, and the Pearson correlation coefficient is dominated by the values here which are far from the average. So that's a little bit of a difference between these two metrics, and which might make one of them more sensitive to certain features than the other. So if you ask me which one is better, I would say I don't know. It very much depends on the type of the images, and ideally it's a good idea to calculate both of them, because then if both of them tell you the same story, then that means that it makes the argument stronger. If there is a significant difference between what ICQ tells you and what Pearson correlation coefficient, then probably it's something where you might be you might look deeper and try to find why it is so and what does it mean for your question which you are asking. These funny images, those are the Icq histograms, and basically what is on the right hand side from this center line, so that's what contributes to colocalization, and what is on the other side, that's what contributes to anti-colocalization. So if there is everything is more shifted to the right, then that means there is a positive colocalization. If it's split evenly, like in this case, where I just rotated one of the images by 90 degrees, then that means there is neither colocalization nor anti-colocalization. And if it's all shifted more to the left-hand side, then that means there is some anti-colocalization in the images, which is what I see here when I have the gradient in opposite directions. So we can have a look at some more realistic images. Yes, that's not what I wanted to show you here. Let's take something more realistic, and I have here an image So this is again an image from the sample images. Already here. Otherwise, you can find it file, open samples, and it is called Neuron 5 channels. So you can see that there are 5 channels, green and red channel, which are quite strongly colocalized. That seems to be the neuron itself. Then there is a blue channel, which doesn't seem to colocalize too much with the red and green. But if I do image, color, channels tool, and instead of composite, I look at the individual channels. You can see red and green are pretty much strongly colocalized. Blue, there is some, you can see the neuron also in the blue channel, but it might be just, this is just a bit of crosstalk. And then you can see in this channel, you can also see the neuron, but then again, the dominant features are outside. So I want to see the colocalization of this neuron. I could use again this colloc2, but I want to show you another plugin, which is also very popular, and it's called JCOP, which stands for Just Another Colocalization Plugin. And again, I need to, before I use it, I need to, don't need these apples and pears anymore, but I will need to image color split channels. And in this case, at first, let's look at, so red neuron channel. What's the matter here? Channel 1 and here channel 2. And now there are, again, I can select which metrics I want to see. I can select that I want to have Costa's automatic threshold. I have, so one difference from colloc2, colloc2 doesn't allow you to set the threshold manually. While here, I can use Costa's automatic threshold, but if it doesn't work for me, I can also set a manual threshold. On the, I can do also Costa's randomization for the statistical significance, where I would have to define the size of the blocks and the number of rounds. So I do analyze. So here you see this is the these are the histograms, the Icq histograms. So you see that it's clearly shifted more to the right-hand side, which is what I would expect for positive colocalization. These are some more fancy things which don't need to, I don't want to confuse you with them. So Pearson correlation coefficient 0.834. So this is quite a high value, not surprisingly. Meanders coefficient, so without threshold close to 1, meaningless, but with this threshold they are still quite high, which is again all makes sense. And the Icq is 0.24. So you see that this is a, in this case, it's again a value which is not that high. And it shows how this Icq is a sensitive, little bit sensitive to different things compared to Pearson correlation coefficient. So especially if you have local variations within the object, like if you see there are some spots in the neuron. So the overall, the neuron, of course, very strongly colocalizes in red and green channel, but there are some spots which are differently localized in red channel and in green channel. And this Icq is more sensitive to that than Pearson. So that's what reduces the value in this case. I can try to, for some reason I don't see the other images, so let's open the plugin again and have a look at the channel 3, that was the blue channel, and let's see how does it look like in that case. And let's see the value. So Pearson correlation coefficient is lower in this case because, of course, there is less colocalization, Meanders, and now you see the difference because here in I can still see the neuron in the blue channel, but these features which are prominent in blue channel are not reflected in red channel. So that's why in the one of this coefficient is quite high, because everything what is in the red channel has colocalizes with something above threshold in blue channel. But not everything which is in blue channel colocalizes with red channel. So that's the difference, and that's the information which can be derived from this Meanders coefficient. And the Icq is, again, it's lower, which is what we expected to be. One thing which I'm missing in Jacob is that it doesn't show me the 2D histogram. So for this reason, I have created a, let's close all this stuff, not to have it so messy here. And I have created a macro to see 2D histograms. So again, I will open this neuron image and I will run my macro. Run, and I can select which of the channels I want to colocalize. So for example, I want to look at channels 1 and 2. I can either set how many bins I want to have, or I have some magical formulas to do it automatically. And now this is the histogram. Let's adjust the brightness contrast to see a little bit more of those less prominent features. And you see it's, as I would expect, for something which is quite strongly colocalized. And let's try to look at the red and blue channel, and I'll show you another feature of this macro. Run channels 1 and 3. Again, I adjust the brightness and contrast. And you can see now that I have here two branches. This one would correspond to those objects or features which are colocalized in the two channels, and this is something which is present only in the blue channel, but not in the red channel. And now it's asking me to select a region of interest. So I can draw a region of interest. Which will, so I only select the part which corresponds to what is in blue channel, but doesn't colocalize with red channel. And what this does is that it will make a mask on the image and only show me the pixels which correspond to these points in the histogram. So I press here OK. And it asks me then, if I press OK, I will have the option to select another region of interest and do this whole thing again. And now I can have a look at the masked image. So red channel basically disappeared, and in blue channel, you can see I still have here those features which are not present in the red channel, but the neuron, which was the part which colocalized with red channel, is disappeared. So that's hidden. Now I can select another region of interest. And this time I can select the part which does colocalize. Okay, so like this, for example, I press OK. And now you see, don't need, so I end the macro. And now what you see is here I see the neuron. Obviously, I am here now missing the part which is mostly blue channel, and here in blue channel I see selectively only the neuron and not these other lines. So this is something where I can, for example, it can help me to visualize those parts of the image where the colocalization happened, or to see which parts are not colocalized. I'll show you one more thing in Jacob. A case, again, comparing the Pearson and Icq. So I have here so I again look at these images of the beads. Image, just brightness contrast, and I'll take, let's say, the first frame, and then I take the last frame. Image, okay. So I have now two images which do not colocalize because the beads have moved in the meantime. And I do analyze, plugins, Jacob. That should be the correct one. Analyze. And let's see, where do we get these outcomes. So Pearson coefficient 0, this is what we would expect. But ICQ, surprisingly, you see quite a high value, 0.32 out, so the maximum is 0.5. So this is something which would sound like a very high degree of colocalization. And this is, again, a case where the ICQ clearly fails. Because if you want, if I do image, color, merge channels, and I make an overlay of these, you see that they clearly don't colocalize, except of maybe one beat, which here there are two beats which overlap partially, but clearly this is not colocalized. The reason why ICQ is high in this case is because there's a very high difference between the beats. They are extremely bright compared to the background. So the average lies somewhere above the background. And I have plenty of pixels here, which in both channels are lower than the background. So if you see here, by definition in ICQ, so if the pixels are lower than background in both channels, then this PDM becomes positive. So that's why they all contribute to the high ICQ value. So while in this case, Pearson clearly will give a value which is 0 and is clearly more robust against this case of the few very bright features which are very far from background. And I think this is, we can close with this. If you have any questions, is there a way to revert to previous version of Fiji? Not an easy way, unless you have a backup. So maybe it was my mistake. I should have made a backup to copy my Fiji folder, and before I did all these updates, and then I could run Fiji from the backed up folder. I haven't done it. I didn't suspect it will go this wrong, considering that I've updated quite recently before. And yes, you can update because Fiji it's portable. So that means you don't have to install it. So it basically runs from the folder which you can place anywhere. So you can even have Fiji at an external hard drive and plug it to your USB and run Fiji from there.